All right, example 2, we are using an analytical graphical approach, and this says we have our calculator active, which remember, calculator active means you should actively be using your calculator. So the rate of change in kilometers per hour, that looks like a rate to me, of the altitude of a hot air balloon is given by R of t. So I'm going to think about R of t as my derivative layer, which means I could talk about the altitude as big R and the rate of change of the rate of change as little r prime. So they're giving me kind of this layer here, which is like working at the derivative layer. We're at the rate layer. We're also looking at the closed interval from 0 to 4, so that's important to note in case I need to find any absolutes, where t is measured in hours. Assume the balloon is initially at ground level, which means at time 0, our position is 0. I should put r of 0 is equal to 0. For what values of t between 0 and 4 is the altitude decreasing? Well, the altitude of the balloon would be the same thing as the height of the balloon. Trying to change colors. Height of the balloon. Well, if this is the rate of change of the height, then this represents the altitude. So I'm trying to figure out when is the altitude decreasing. Well, that means that I want to know where is the derivative of big R, aka little r. Where is little r of t less than 0? Well, convenient for me, I have a calculator. And I have an equation, not that equation. I have an equation of t cubed minus 4t squared plus 6. I'm going to do a little zoom 6 action. Oh, look. Beautiful. I want to know where this graph, which is r of t, I'm looking at it, where this r of t is negative. Well, it looks like we're going to be everywhere we drop below the x-axis. I need to figure out what are these zeros. So second trace, looking for a 0. This 0 looks to be between 1 and 2. So I'm going to get a left bound of 1 and a right bound of 2. And I'm going to guess it's happening at 1.5. And I was so close, it's 1.572. So starting at 1.572 is where I drop into negative territory. And then I'm actually going to teach you how to store this. I'm going to remind you how to store this, rather. So right now, your calculator has this value in its memory, 1.5719933. I'm going to go to my home screen, so second quit, and I'm going to store this as alpha A, just so that I have it. Next thing then, if I go back to that graph, second trace, looking for the other place that I crossed the x-axis, looks like that's somewhere between time 3 and 4. So my left bound will be 3, my right bound will be 4. I'm going to guess 3.5. Oh, look, it's 3.154. So the altitude of the balloon is decreasing between these two values. Again, I'm going to go second home, and I'm going to store as B, just so I have these as reference points. We'll use those later. All right, but again, altitude decreasing, which means R of t would be negative. All right. Next thing, find the value of R prime of 2 and explain the meaning and the answer of the context of the problem, indicate units of measure. First of all, reminder, answer in the context of the problem means I need to reference the hot air balloon's height. Okay? R prime of 2, I'm going to start by finding R prime of, oh, actually, wait, I have my calculator. Let's work smarter, not harder. If I wanted to find R prime of 2, I can just do math 8, take the derivative of alpha, oop, no, try again. Take the derivative of alpha trace, there we go, y1, and I want to find that derivative at 2. Negative 3.999. Hopefully we are all smart enough to know that that really means R prime of 2 is equal to negative 4. Now, for this one, could you have found the derivative and then subbed into? Yes, you could have. The derivative here isn't that bad to find, but I'm going to let my calculator do the work. So R prime of 2 is equal to negative 4, and that's going to be the rate of change of the rate of change. So that's going to be kilometers per hour, also known as kilometers per hour squared. This means that the rate of change of the altitude, which was the little r of t, is decreasing at t equals 2. Okay, so I've referenced the altitude. I'm referencing the context of the problem. Next one, what is the altitude of the balloon? Trying to change colors, come on. What is the altitude of the balloon, so big R of t, when the balloon is closest to the ground, which means when we have a minimum altitude, somewhere between 0 and 4. Well, let's think about our minimum. If I look at my graph, between 2 and 4, I'm going to have a minimum when little r changes from negative to positive. Well, that was stored for me. I'm going to be closest to the ground at t equals 3.514, right? I already found that up earlier. So I'm looking for the altitude at that moment. Well, I know that my altitude at 3.514 will be equal to my altitude when I started plus a collection of all of my changes over that interval. Little r of t was the change in altitude. Okay, well, now thinking about this, r of 3.154 is what I want. I want the altitude at this moment. R of 0, I was told the balloon is initially on the ground. And this, well, how lovely, I have a calculator. We usually do math 9, which is great. You totally can. I'm going to also show you, though, when you have the graph already drawn, watch this funness. Funness? Sure, funness. Second trace, number 7. And I can find the area between 0 and 3, actually even fancier, and alpha b, because I had it stored. There it is. Looks like my altitude is 1.348. Sorry, my displacement is 1.348. Right? Which means that my altitude at time 3.514 is 0 plus 1.348, which is really just 1.348 kilometers. All right, number 4. Find the value of this and explain the meaning of the answer, the context of the problem, indicate units of measure. Well, I know how to do this. I'm going to go second trace, number 7. This time I'm going all the way from 0 until 4. And I get 2.667. 2.667. This is going to be kilometers because I'm collecting the change in altitude, which will give me my current altitude. The other way you can think about this is the integral from 0 to 4 of the rate of change is equal to the net change in the antiderivative. So my ending altitude minus my starting altitude, which would be my displacement. Indicate units of measure, I did that. Displacement is the concept. In the context of the problem, I should say the balloon is 2.667 kilometers off the ground because our reference point was the ground, and so we are 2.667 away from our reference point. Next one, find the value of this integral and explain the meaning of the answer in the context of the problem, indicate units of measure. Well, I don't want to look at this graph anymore. I want to look at the absolute value graph, or I can just do math 9, going from 0 till 4. And absolute value, the quickest way to get there is to go to second 0, which is your catalog, ABS, alpha trace, y1, with respect to x. You also could retype in your function if you wanted to. Here is my integral. I get 11.529. Because again, I'm integrating a rate of change, right? So this is collecting kilometers per hour, and then dt would have been measured in hours, and I'm collecting all of those. So my hours cancel, and I'm left with kilometers. I'm working a layer backwards. Because I'm accounting for all positive rates of change, this represents my total distance traveled by the balloon. We got to talk in context. On the interval from 0 to 4. Okay? Total distance traveled. Last question. Must be on the next slide. There we go. What is the maximum altitude? The maximum on the closed interval from 0 to 4 should indicate a candidate's test. So my times are 0 and 4. I'm looking for the altitude, so big R of t. My critical numbers I already found in the very first question. I had something interesting happening at 1.572. It was where my derivative was 0. And at 3.514 was also where my derivative was 0. If we go back to our graph, right, where is this derivative equal to 0? Those were our two critical numbers. Well, now I need to do a candidate's test. Okay? If I wanted to find R of 0, that's going to be equal to, well, 0, because I start at the ground level. It's not very exciting. If I wanted to find R of 1.572, that's going to be equal to where I start plus a collection of all of my changes, which was little r. If I wanted to find R of 3.514, I would say, well, where did you start? Plus a collection of all of your changes. Finally, if I wanted to find R of 4, I would find R of 0, that's an R, all of the collection from 0 to 4 of R of t, right? Where you end up is equal to where you start plus a collection of all of your changes. Well, we already found some of these. In question 3, we found this one was 1.348. That was our altitude at the minimum. We already found this one. In question 4 was 2.667. The last one then we need to find is this one in black. And if you do this in your calculator, Math 9, you end up with 5.779. So what is the maximum altitude of the balloon? The maximum altitude is 5.779 kilometers. And remember, your candidate's test serves as your justification for that. Let's think about this balloon and its path. We start at a position of 0 on the ground, right? We're initially at the ground. This is my velocity, my rate, my derivative graph. So I have positive rates of change, which means my balloon is going up, going up, going up. Then my balloon goes down and then back up. So look at our position function. If I were to graph the altitude of this balloon, R of t and t, I'm at 0, I'm at 5.779, I'm at 1.348, and then I'm at 2.667. Because my velocity was positive, then negative, then back to positive. Here's my minimum when I was closest to the ground. Here's my displacement, because my start was 0. And here is the maximum altitude that I reached. It was at time 1.572, and it was a maximum height of 5.779.